ahead.
Yeah, well, thank you very much. And as I said, I mean, it's early. I hope I will survive this talk, and you too. So I do my best. Well, thank you very much to the organizers for giving me this great opportunity here to talk. We'll talk about some recent work, mostly done together with Todd Oliynyk from Monash, and it's based on earlier work that I've done with Philippe Lefloc and Ellery Ames and Jim Eisenberg also. So as the theme of this conference here is it's supposed to be about matter and general relativity. So I want to talk about matter in cosmological spacetimes. And as the title suggests, I particularly want to focus on the past asymptotics. So the asymptotics near the so-called Big Bang. So where the cosmological background, where the cosmological spacetime becomes infinite or blows up in some ways. And so I'm particularly focusing on this, on the past asymptotics. And for today, I'm focusing completely on a result that is fluids on fixed cosmological background. So I'm not talking about today I'm not talking about the coupled Einstein matter situation. So just the matter equation on fixed cosmological backgrounds. The coupled Einstein matter case is currently work in progress. So being in a cosmological setting, in mathematical cosmology, that means that the spatial topology is compact, and today I completely focus on just the three torus. So whenever you see sigma, that's my spatial domain, that's the three torus. So I mean, many of these questions that I'm trying to address today are of course motivated just by geometry and PDEs, but they're also motivated by physical cosmology, where it is really an open question what the consequences are of the full nonlinear nature of Einstein's theory. So for example, regarding the matter in physical cosmology, people often assume that that the matter is co-moving or close to co-moving, which means that all the peculiar motion of the matter is very small. So the matter doesn't really have its own or very little own movement. It just follows the overall expansion of the universe, and whatever own movements or whatever peculiar motion there is can be described by linear equations. And but of course the equations are nonlinear, so it is an open question whether the linear equations are good approximation. Right. So I've talked about fluids on fixed cosmological background spacetime. So now let me say what kind of background spacetimes I'm considering here. So over the last decades, in particular the last few years, we've learned that it is probably a good choice to think of spacetimes as solutions of the Einstein-scalar field equations as opposed to just the Einstein equation or just the Einstein matter equation, because the scalar field has sort of the way to make the Big Bang asymptotics much simpler. I don't have much time to talk about this. So I'm looking at background spacetime. I'm looking at solutions of the Einstein scalar field equations. So I have a background matter field, namely a scalar field. And the particular solution that I'm looking at are the Kasner scalar field solutions, because they naturally arise in this context as sort of the limits at the Big Bang. And so the scalar field for this particular class of exact solution is just a log of a cosmological time function, T tilde here. So T tilde equals 0 is the Big Bang. This is where the universe is in some sense infinitely small. So this is where singularity is. And then we're looking at positive times T tilde. That's the sort of vicinity, the neighborhood, the early universe, the neighborhood of the Big Bang. And then A here is just a parameter, which measures the strength of the scalar field. And the metrics for the Kasner scalar field solutions are spatially homogeneous, but in general not isotropic, because each spatial directions come with a different scale factor here, which is a power of t, and these powers here, these pi's, are called the Kasner exponents, which is another set of 3 parameters for these background spacetimes. But these, in total, 4 parameters, so the Kasner exponent and the scalar field strength A here, are not completely free. They have to satisfy these Kasner constraints down here. And then there are important special cases. One special case is the Kasner-vacuum solution, when this parameter A here happens to be 0. So when there's no scalar field, this is the case where the Kasner exponent, by virtue of these two relations here, are sort of the least restricted. And in fact, this gives us the most, in general, the most anisotropic kind of solutions, background solutions. While in the sort of opposite extreme case, when the scalar field parameter is as large as it can be according to this interval here, so the endpoints of this interval here, then the Kasner exponents are completely constrained by these two conditions here. And in fact, they have to be the same. So all of the Kasner exponents have to be 1/3. In this case, the metric is therefore isotropic, and we get a flat Friedmann-Robertson-Walker solution. So from the physical cosmology perspective, this case down here, so the flat Friedmann-Robertson-Walker case, is the most important one, I guess. But for us, and from the conceptual point of view, solutions anywhere in the regime between the vacuum case and the flat Friedmann-Robertson-Walker case are relevant. So the result will hold for all of these. Okay, so this is the background spacetime, and which models the early universe, the Big Bang singularity at t tilde equals 0. And now I want to solve the relativistic Euler equations on such a background spacetime. So I'm really talking about the full compressible relativistic Euler equations. And I'm going to assume an equation of state, which is maybe the most common one that people use in cosmology, where we assume that the pressure is just linearly proportional to the density of the matter. And the proportionality constant here just happens to agree with the speed of sound. So the speed of sound parameter Cs, it's a principal pre-parameter in our models. And in physical cosmology, they have particular favorite values for the speed of sound which they use, and I will come back to that later. But in principle, the speed of sound constant here is an arbitrary parameter. I will have some restrictions about this in a moment, but for the moment, the only thing that pops out immediately is the restriction that the speed of sound should be larger than 0. The dust case Cs equals 0 makes the equation quite singular, as you can see almost directly down here. But that's something we don't really need to worry about, because we will have other restrictions on Cs later. And now, I mean, Gerald Speck gave us these beautiful lectures about the Euler equations, and he gave us a few examples of how we can write the Euler equations. Here's another one, which we are using, which is due to Frauendiner and Walton. And the idea here is that the Euler fluid, so the fluid, can be represented just by one, in general, not normalized vector field V alpha. So this vector field V here contains all the information about the fluid. So the standard fluid vector field, so the normalized fluid vector field U, which is often called U or so, is just obtained by normalizing this vector field V here. And the pressure and the density is obtained from essentially the Lorentzian norm of this vector field. Okay, so this vector field V, being non-normalized, contains all the information about the fluid with this particular equation of state here. And what is so nice about this formulation of the Euler equation is that it can be written in this form of transport equations here, where these matrices here are explicitly symmetric. So for each delta here, so each derivative, we in front of each derivative, we have a bilinear form, so alpha beta here, which is explicitly symmetric. And in fact, we get a nice positive energy for extract a nice positive energy from that, which we can use to analyze the fluid. I'm not claiming here that it's strictly necessary to write or to use this formulation here of the Euler equation to prove our result, but it somehow has turned out to be useful. So in the result, you will often see this vector field V here, which I often call the Frauendiner-Walton fluid vector field. Okay, so my plan for this talk is now to show you the result that I've obtained together with Todd Oliynyk. And first, I want to show you the result just in a sort of informal manner, just to show you, so discuss what's happening and discuss a little bit of interpretation and also some open questions. And then in the second part, I'm going to show you the precise versions of the result and talk a little bit about the proof. So let me first just give you an informal version of our result. And as you will see in this talk, I just copy things from our paper. I don't expect you to read all these words on this slide here. I will take you through this step by step. So the first thing that we assume, as I've already discussed now, is that we have a given Kasner-scalar field background solution with parameters A, P1, P2, P3, which satisfy this Kasner constraint. But in fact, this is not so important. In fact, the result would also hold if the Kasner constraints would not hold. Then we have this funny restriction here. And in some sense, I guess this is maybe the most interesting part of this talk here, is that we have identified these kind of restrictions here. So this is now an inequality that we assume in the whole talk that relates the speed of sound parameter here and the Kasner exponents. Okay, so I mean, one set of the inequality is just that one is smaller than CS squared, which just means the speed of sound of the fluid is smaller than the speed of light, which just means that the fluid is not stiff, which is maybe a natural assumption, given that we know that stiff fluids have quite a different behavior than non-stiff fluids. So the interesting part of this restriction is really the second inequality here, CS squared larger than all the Kasner exponents. And I want to, in this informal version of the theorem, want to show you where this one is coming from and what the relevance of that restriction is. So what we find is, or what we essentially prove, so just informally at the moment, is that all the solutions of the Euler equations near the singularity of the Kasner-scalar field spacetime, so near t tilde equals 0, can be written in this formula. So this is the Frauendiner-Walton fluid vector field, and I've written it here in terms of an orthonormal frame of the background spacetime. So E0, E1, E2, E3, just an orthonormal frame of the fixed background spacetime. So it's, if you wish, an orthonormal reference frame that we carry around. And then we write it in terms of these functions W0, W1, W2, W3, which very roughly speaking, we prove to be convergent at t tilde equals 0. Because these are nicely behaved bounded functions which converge at t tilde equals 0. And then the dynamics is essentially described by these factors in front of the spatial components here, these powers of t, which, and now you see the first time where this condition up here comes from, right? Which by virtue of these conditions here, these powers are all positive. Okay. So what does that mean? So let me just rephrase or summarize what we have here. So the inequality that we had before that appeared in this result that I've just shown you, let me just rephrase that slightly by making from now on this assumption on the Kasner exponents here. So I'm just going to assume an ordering of the Kasner exponents, that P3 is the largest one, P1 is the smallest one, which I can always do without loss of generality. So my condition that I will call stability condition then looks like this here. And now let me, instead of using this functions W that I've just shown you, let me introduce this quantity Qi here, Q1, Q2, Q3, which is just defined by normalizing W1, 2, and 3 by W0, and then multiplying with the power of t that we've seen before, which by virtue of this condition up here is positive. So according to this, if we now normalize this Frauendiner-Walton vector field that I've just showed you, this will give us the normalized fluid vector field here. This then takes this form. Right? So what we see here is that what the role of these Qs is, Q1, Q2, Q3, they are the factors in front of the spatial components of the fluid flow here. So what they are, they describe the peculiar motion of the fluid. If these Qs were all 0, the fluid would be co-moving. That's how a physical cosmologist would interpret that. But if these Qs here are non-zero, then the cosmological matter has its own motion, its own peculiar motion. So Q1, Q2, Q3, measure the peculiar motion. And we see that the normalization here requires that the squares of the q's, the sum of the squares of the q's has to be smaller than 1. Otherwise, the fluid is not time-like again. And what we essentially prove, so, and I will, as I said, I will talk about this in a precise version in a moment, is that all of these qi0 quantities, so all of these peculiar motion quantities here, under this stability condition here, converge to 0 at the cosmological singularity. Okay. What this means is that the fluid is well behaved and stable, and I will quantify that in a moment, but in particular also asymptotically co-moving. So whatever peculiar motions there are at some finite time away from the Big Bang, as you approach the Big Bang, all these peculiar motions die out. Okay. And the density and pressure we can also extract from the Frauendiner-Wharton vector field, and they both behave as you would expect. So essentially, what I'm saying here is that under this stability condition, we can prove a result for the fluid that is very much compatible with the sort of standard picture in cosmology. So in particular, we confirm that that peculiar motions of the fluid, if they're small at some time, they stay small all the way to the singularity. So in some sense, that's a quite nice result. But of course, we do have this restriction up here, what I call the stability condition. So the question now is, do we have to worry about that? Is that a significant restriction or is it not? And I think it is a significant restriction. But it is, I want to also claim that it is a real restriction. So it is not just a technical restriction. So it is a significant restriction because when we look just at the special case of when the Kasner-scalar field background is a Friedmann-Roberts-Walker solution, so when the scalar field parameter is maximal in modulus, so then the stability condition just reads so that CS squared is larger than 1/3, and the speed of sound 1/3 is one of the favorite choices of cosmologists for the early universe. Maybe that's a so-called radiation fluid. So what this tells us is that the radiation fluid is just borderline excluded by our result, just exactly at the borderline of this condition. Okay, that sounds like disappointment in some ways, and so it's of course now a natural question to ask also what happens when our stability condition is violated. And what we want to say is, in general, I don't know what happens, but we have a simple example where we see that there's really something essentially happening different happening when you violate the stability condition. So here it's just a very simple example where I've just assumed that the fluid is spatially homogeneous, so the fluid variables do not depend on the spatial coordinates, and that we have no fluid flow in the 1 and 2 spatial direction. There's only a fluid flow in the 3 direction, which, if you remember, by assumption is the direction of the largest Kasner exponent. And so in this very simple situation, we can implicitly solve the Euler equation. So we get a implicit solution for Q3 here. And where you see that this power of T tilde appears on the right-hand side again. And if this power is positive, so if our stability condition holds, we get exactly the behavior that we prove in our general result. So that's, of course, good. If now this stability condition is violated, so this power on the right-hand side here becomes negative. Unless my constant C here happens to be 0, the right-hand side will, of course, blow up in the limit T tilde going to 0. And then you can convince yourself that the only way that this works is that on the left-hand side, this denominator here goes to 0. So 1 minus Q3 squared goes to 0. And I don't know if you remember that, that means that in the limit when T tilde goes to 0, the normalization of the fluid vector breaks down. So we call this asymptotically null. But physically, what this means is that the peculiar fluid motion is now unstable. So if there's a little bit of peculiar motion at some positive time, so a little bit of Q3 at some positive time, now as you approach T tilde equals 0, this peculiar motion will grow. So this is then inconsistent with sort of the standard assumption of the standard model of cosmology. And then we also, of course, have the borderline case here between. So I want just sort of critical behavior depending on whether this inequality holds or the inequality is violated. That was observed, to my knowledge, the first time by Philippe Lefloc and myself in a study where we looked at the Einstein-Euler equation, but just in Gaudy symmetry a few years back, where we identified this behavior already. And now we find this without any symmetries as well. So there's definitely something. I mean, this simple example here suggests that there is really something about this inequality here. If it's violated, then we probably, in general, we get quite different behavior. But from now on, we'll focus on the case when this inequality is not violated, so when it's satisfied. And I want to show you now more precisely what we actually prove. Okay, before I can do that, let me just do a few preparations. So for the rest of this talk here, I'm not going to restrict to the Kaser-vacuum case, so where the background scalar field parameter is just 0. And it's just that the results can be presented. In this case, the presentation of the result is most easy, but in some sense, it's also the hardest case because the background spacetimes tend, in this case, tend to be most anisotropic. But in any case, all the results also hold when A is not 0. And now and then in our result, we have decided to introduce a coordinate transformation. So before, my cosmological time was called T tilde, and now it's called T. And then there's the natural coordinate transformation, which I'm not writing down now, which brings the Kasner-vacuum metric to this form here. So in terms of this new cosmological time T, which also when it's 0, we have our cosmological singularity. And all the Kasner exponents, so the 3 Kasner exponents are now expressed in terms of one single parameter K. So, I mean, it is not, I mean, in hindsight, it's not completely clear if this was the best choice of coordinates to prove our results, but it has worked. Initially, the motivation to choose these coordinates here was because we had this result by Philippe Lefloc and myself in Gaudy symmetry. And in Gaudy symmetry, it's particularly natural to choose coordinates like this here, where you bring sort of the time and one of the space coordinates on the same footing. For our result here, where we don't have any symmetries, it's not so clear why this, or whether this is really a good choice of coordinates, but nevertheless, that's what we chose, and that's how we proved our result. And now in this time coordinate here, it is now useful to, instead of looking at just these time exponents here that we've seen before, is to renormalize these time coordinates by 1 over 1 minus P1 and call these the fluid exponents gamma 1, gamma 2, gamma 3. So remember, I don't know, I haven't actually said that, but all the Kasner exponents I assume to be smaller than 1 by virtue of my stability condition. So this denominator here is finite, and by virtue of the stability condition, also each of these numerators here is positive. The denominators are also positive, so all these gammas here will be positive. And because I assume that P3 is the largest Kasner exponent and P1 is the smallest one, gamma 1 will be the largest fluid exponent, and gamma 3 will be the smallest fluid exponent in all of the following. And what we then do is we express our Frauendiner-Wharton fluid vector field in terms of these coordinates now, and just consider the coordinate components of this vector field as our fundamental unknowns. Okay, so V0, V1, V2, V3 are the coordinate components. Okay, so now here is result number 1. And again, don't worry about the details. I will take you through the details step by step. But before I go through this result here, I want to let me say that I will present our result as 2 separate theorems. So this is theorem number 1, and you will see why I do this in a moment. The first theorem will be about an application of the so-called singular initial value problem, or the forward problem for the Euler equation, where we prove the existence of solutions parameterized by their asymptotics. So by asymptotic data. So we essentially start on the singularity, evolve forward in time. And then the second result is that we then show that each of these solutions that I get in this way is nonlinearly stable. And the way I show this is by taking Cauchy data here, perturbing this a little bit and evolving backwards in time towards t equals 0 in our second result. So the first result is about forward evolution. The second result will be about backwards evolution. So that's why I split this into two. And I will explain what I mean by this in a moment. So, okay, so this is the singular initial value problem, often abbreviated as SIVP. And maybe the first thing that you notice here is now this condition in terms of the fluid exponents that I've just introduced, gamma 1, gamma 2, gamma 3. This turns out to be exactly equivalent to my stability condition that I had before. So just rephrasing the stability condition in terms of these gammas here. And so maybe in the first read of this theorem, don't look at all the technical details yet. I will take you to some of them later. Let's just talk about what we actually do when we solve the singular initial value problem. So the singular initial value problem means that we're choosing data that we call asymptotic data, which is just 4 functions for each component of the fluid. So these are functions defined on our spatial domain sigma, so on the 3 torus, with some regularity here. So, and we assume that the time component, so the 0 component of this data is positive. And then what we prove is the existence of a Frauendiner-Wharton vector field, a solution of the Euler equation, that exists all the way from the singular time t equals 0 to some positive time t0 here. And this solution is characterized by the following fact, namely that when we rescale the fluid components, each fluid component by an appropriate power of t, so you see that each component here comes with a power of t that is given in terms of these fluid exponents here, that these rescaled functions, each of these rescaled functions converges at t equals 0. And it does not just converge to anything arbitrary, but it converges exactly to our asymptotic data. Okay? So this is how this, the solution whose existence we show here is characterized by the fact that that these rescaled functions here converge to the initial data, to the asymptotic data function. And they converge in a rate with a power eta here that we can estimate up here completely in terms of the fluid exponent. I will say a little bit more about that. So let me just tell you that this statement here, this convergence statement, is exactly equivalent when we go back to the informal version of the theorem that I've shown you at the beginning. So when we write this result that I've just shown you, again, in terms of an orthonormal frame of the background and in terms of the original time coordinate t tilde here, then the result number 1 can be phrased as follows. It's phrased that these W0, W1, W2 functions here, they converge to prescribed limits, W0 star, W1 star, etc., etc. Okay, so this form of the vector field with these functions here would have a limit that is exactly equivalent to the convergence statement in our theorem. And okay, so let me summarize what we have so far, and I would go back to the theorem in a moment. But this result was originally motivated by a result by Philippe Le Floch and myself before, where we solved the coupled Einstein-Euler equation, but only in Gaudy symmetry. Okay, and then we found exactly the same kind of result. We solved the singular initial value problem, and because of Gaudy symmetry, in that case, we only had one of these fluid exponents that was relevant. Now we have all the 3 ones, but it is sort of a natural starting point. Was a natural starting point for us. And this is as I said, a singular initial value problem in the mathematical GR relativity literature. This is also often called the Fuchsian problem or Fuchsian method. And over the years, many people have proven theorems about singular initial value problems. And I think the first one was by Alan Randall and Hichan Asami in the constructed certain class of analytic solutions. And over the years, people have come up with new theorems that provide solutions to that kind of problems here in also with Sobolev regularity for hyperbolic equations, for hyperbolic Fuchsian equation. And we have used the latest version of that kind of theorem here by Todd and myself. And one of the motivations was that to come up with a theorem for the singular initial value problem for Fuchsian equations which is exactly in the same framework, use the same assumptions as a corresponding theorem that we proved earlier for the so-called backward problem, so for the Cauchy problem towards the singularity. So the point was that we can solve the singular initial value problem and the complementary backward problem using the same set of assumptions and so on. And I will talk about this again later. And the essential strategy for this kind of singular initial value problem is as follows. So to prove these, it's sort of an involved iterative process where you, so given asymptotic data, right, the first thing is you derive approximate solutions. So these are functions VL, where L is some integer order, that satisfy the equation with an error that can be bounded by some positive power of t that grows as L grows. Okay, so the larger L is, the better this approximate solution satisfies the equation. And this kind of approximate solution can be in general constructed by some iterative procedure. And when we have an approximate solution of some order L here, then we construct the remainder quantity. So we take the actual unknown of the equation, subtract the approximate solution from it, which intuitively means that we get a function that is that decays like some power of t that is larger the larger L is, right? So the better the approximate solution is, the more these two functions should agree at t equals 0. And then we scale off some of this decay with some positive choice of mu here, and define this also our remainder. So, and then we write the equation in terms of this remainder and hope that the equations take this characteristic Fuchsian form. Characteristic Fuchsian form, I mean that we get this 1 over t singularity here. So that's the characteristic Fuchsian kind of singularity. So 1 over t, where we have a matrix here that multiplies the remainder here. And we have a lot of other terms in here, in this junk term here, if you wish. And the point is the following, that by choosing this L here sufficiently large, I hope that I can choose mu sufficiently large. And that will mean that I can make this matrix B here as negative as I like. Okay, and in particular, I can make this matrix B here negative definite by choosing a sufficiently an approximate solution here of sufficiently high order. And when this matrix B here is uniformly negative definite, then we can use standard L2 based energy methods to derive estimates here. Well, if of course this junk term here is sufficiently well behaved, and that's where all the technical kind of conditions go in these kind of theorems. But essentially the idea is then that we can then prove estimates, energy estimates, which make sense forward in time. Okay. And the point that we have to construct this approximate solution here of sufficiently high order to make this B here negative definite, this is now in this precise result number 1 here, the reason why I have this parameter L in here. So L essentially measures what order of approximate solution we had to use to prove our result. So to close the estimates to get this matrix B negative definite. And so you see that there's therefore a discrepancy between the differentiability requirement for the asymptotic data and the differentiability of the solution. Okay, so there's actually a loss of L derivatives here, where L is can be estimated in this particular way quite explicitly in terms of the fluid parameters. So in particular, we see that the fluid, that this parameter, sorry, this loss of differentiability parameter L here, if you wish, has to be larger the closer our inequality is sort of to the endpoints of this inequality here. So the closer gamma 1 is to 1, right? So this 1 minus gamma 1 becomes small, or the closer gamma 3 is to 0. So this quantity becomes very small. So in all these cases, L becomes very large. Okay, so this is the origin of this parameter L here. And another thing that I just want to mention for now, which will become later in just a moment, important in just a moment, is this uniqueness result that we also prove here for this, which says that suppose I have a solution of the singular initial value problem for some choice of asymptotic data, V, And then suppose I find another function, v tilde, that is the solution of the equation, that agrees with v to some sufficiently high order in t, so this is what this estimate says here, then v and v tilde actually have to be the same. So this is sort of the corresponding, the uniqueness result corresponding to uniqueness for the Cauchy problem. Okay, so this is our result number one. So now we have this family of solutions of the Euler equations parameterized by asymptotic data. And now in result number two, I want to show you that each solution in this family is non-linearly stable. What do I mean by this? So that's what I want to discuss now. So here, as I said, talking about stability now, and I will solve the so-called backward problem. So I will, as you will see in a moment, now evolve backwards towards the singularity. So maybe in the first instance, ignore this parameter L0 here, where L is, this integer L here is the same that we have seen in the previous result. So we start this result again by picking asymptotic data. So this V star. And maybe in the first instance, just assume that this L0 here is 0. Okay, that L0 is not there. So you have K plus L as you had in the previous result up here. And then by virtue of the previous theorem, we get a solution of the singular initial value problem that are now called VS, like singular initial value. This solution, we prove, exists on a time interval from t equals 0, right, from the singular time all the way to some time t naught. And what this means is I can then take the value of this solution at t naught and interpret this now as Cauchy data. And if I would now solve the Cauchy problem with that Cauchy data backwards in time, I would of course get the same solution VS. So that would be boring. So what I'm doing now is instead I'm going to perturb those Cauchy data given by the solution of the singular initial value problem by some function v0 or by some field v0. And the only restriction on that perturbation v0 for the Cauchy data is that it has to satisfy a certain smallness condition. Where delta is a smallness parameter. Okay, so we're looking at arbitrary but small perturbation of the Cauchy data induced by the solution of the singular initial value problem at some regular time t equals t0. And with this Cauchy data now, I'm going to solve the Cauchy problem, and I'm going to solve the Cauchy problem from the initial time t0 backwards in time to t equals 0 and see what kind of solution I get and what the solutions do. And what we prove is that the solutions of the Cauchy problem, which we call VC now, so C like Cauchy problem as opposed to VS like solution of the singular initial value problem, all of these solutions exist globally in time. So they exist all the way from t0 to 0. So they don't blow up or anything before they reach the cosmological singular time. And even more, the fluid components converge. So when we rescale each of the fluid components by exactly the powers of t that we expect, I think this is a typo here, this is supposed to be gamma 1 here, then these quantities converge. Okay, and we get estimates for the how fast these limits are attained. Okay, so again, this kind of statement about the convergence, when we rephrase that again in the language of that we use for the informal version that I showed you at the beginning, what this means is that, so we express everything again in terms of the cosmological time t tilde in the orthonormal frame here. Then these functions W0, W1, W2, W3 for these perturbed solutions converge to some limits. So that's the equivalent statement. So up to there, let me just summarize what we have up to there. Up to there, we have small data global existence backwards in time. Small data meaning smallness of the perturbation. Okay, the solutions that we evolve backwards in time are not at all small because we're perturbing solutions of the singular initial value problem at that time t0, which doesn't have to be small. Okay, so the smallness is the parameter of our perturbation. And then we get relatively precise asymptotics here, the existence of limits at t equals 0. So this is a nonlinear stability result of solutions of the singular initial value problem that we obtained in our result number 1. However, we prove more than that. I want to explain that now, because the estimates that we find in result number 2, so the one that I've just shown you, turn out to be sufficient to apply the uniqueness result of result number 1. Okay, which was, if we go back to result number 1, was this one down here. Okay, and what this allows us to prove is this last part of result number 2 here, which says that the solution of the Cauchy problem, so these perturbed fluid solutions, turn out to agree again with the solution of the singular initial value problem. But of course, this is not the same solution of the singular initial value problem that we started with up here. It is now the start with up here that was characterized by these asymptotic data. This is now a solution of the singular initial value problem characterized by new initial data, namely which agree exactly with those limit functions. Okay, so what this shows you is that when you perturb a solution of the singular initial value problem, you get again a solution of the singular initial value problem, just with some perturbed asymptotic data. So each solution of the singular initial value problem, therefore, is an open neighborhood of solutions of the singular initial value problem. And I will talk about some caveats with this open neighborhood here in a moment, but this is what we get at this stage. So to a large part, this theorem here is an application of a theorem that we proved, so Todd and his student and myself proved for quite a large class of singular Fuchsian equation, and it's about small data global existent backwards in time, exactly proving this kind of existence, which is sort of the complementary result that we use to solve the singular initial value problem for result number 1. It uses very similar sets of assumptions and so on. So there's some synergy between these two results. That's what why it's quite a nice framework, in my opinion, here that we use it. And but this theorem by itself does not give us the full result. And let me just tell you, essentially, this theorem by itself applies to the case when this L0 parameter that I've just set to 0, that just sort of said we can assume to be 0. This holds in the more general case, or can be applied in the more general case when L0 is 0 or anything positive. So you see that this L0 appears everywhere in these for these differentiability assumptions here. But if under this more general assumption than the one that I've crossed out here, we can only show the following. So we can show the global existence of solutions, and we can show that the time component of the fluid was scaled with this power of t here converges, and we can show that the time component converges to this limit with a particular rate here, but we cannot show, just with this assumption here, that the spatial components of the fluid converge as well. We will get a different kind of estimate here that just says that certain other rescalings of the fluid decay. So we get a weaker result when we just assume this S0 equals, say 0 or any positive number, and where we just apply this theorem by Todd and his student and myself. So the second part of the proof is then therefore to make stricter assumptions on the regularity here and use this additional regularity to improve the asymptotics so that we get these limits here in particular. And this can be done. I mean, this is sort of the most technical part of the proof, I guess, where we iteratively improve the asymptotic at the cost of regularity. So, I mean, what I mean is, so by application of this theorem here, we have some sort of base estimates, which give us relatively inaccurate description of the asymptotics. And then we take the equations again and now interpret this equation essentially as an ODE, where we put most of the terms into a source term. And by virtue of these base estimates that we have from here, we estimate the source term and solve the ODE and hope that we get better asymptotics for the solution of that ODE. And we do, but every time we do this, we lose essentially one derivative, because all the spatial derivatives terms are then interpreted as a source term. So this means that we lose one order of regularity here. And so what this L0 parameter is, it tells us how often, given the base regularity that we get from our base theorem, how often we have to iteratively improve the asymptotics before we can prove the existence of these limits here. Okay. Right. So this is this. Now let me summarize these results quickly in this form here, where we go in particular talk again about this loss of differentiability in each step. So result number one, this was about the forward problem, where we take asymptotic data, we evolve the solution of the single initial value problem forwards in time to some time t0, and interpret the value of the solution at that time as Cauchy data. And if you remember that, I don't know if you do, we discussed that result number one tells us that in this process, we lose L derivatives. So we have k plus L0 here, say, for the asymptotic data, then the Cauchy data will be in hk plus L0. And this loss of L derivatives come from the fact that I have to, in order to prove the result about the single initial value problem, I have to construct an approximate solution of order L. In every time, for each order, I lose a derivative, essentially. So in this map here, I lose L derivatives, taken from asymptotic data to Cauchy data. Now, for result number two, which was about the backward problem, I can interpret this as a map from Cauchy data to asymptotic data, which says now if I take Cauchy data, so say the Cauchy data up here and perturb it, that's our perturbation parameter. This is in some space hk plus L0. And I solve the Cauchy problem backwards in time towards the singularity and construct the limits. The limits will in general be in hk plus L. That was. So for this map here, I lose L0 minus L derivatives when we go from Cauchy data to asymptotic data. So when we look at this sort of round trip here, starting from asymptotic data to Cauchy data to Cauchy data, and then from Cauchy data back to asymptotic data, you see that in total I've lost L0 derivatives. So so we can convince ourselves that the forward map is at least locally the inverse of the backward map. However, because of this loss of differentiability, this map is therefore definitely not a homeomorphism in a Sobolev topology, right? Because these two spaces here do not agree. So, I mean, you could wonder now, is this just because our techniques are not refined enough, or is that a general property? And there was this very pioneering work, as far as I know, by Hans Ringström, who showed that even for simpler classes of equations than this fully nonlinear or quasi-linear system of Euler equations, like for example wave equations or so, linear wave equations with constant coefficients or so, he was able to show quite explicitly that this is this loss of differentiability is quite a common feature. In general, there can even be, you can even win differentiability sometimes, but the loss of generality is also something that you see in many cases. So it's not completely surprising that we find the same here. Of course, our results here are not as, for this nonlinear equation here, are not as sharp as Hans Ringström's work for the linear equation, but in general, it's not a surprise that we see this loss of differentiability here. So what Hans Ringström then pioneered is then the question whether we can at least show that these kind of maps here are homeomorphisms in the C-infinity topology. So basically, where you take these differentiability conditions here to infinity. And I need to say that our results here do not give that, or we cannot conclude this result from our theorems. And the reason for that is that in our proofs of the theorems, we have not paid careful attention to the dependence of all the constants on the differentiability parameters. So it might very well be true that some of the constants that we find degenerate in the limit when these differentiability parameters go to infinity. So basically what we are currently doing is just going back to our work and sort of following through all the steps and see that all the constants that we get can be estimated uniformly in the differentiability parameter here. So at the moment, this is an open question whether our result for the fluids on Kasner-scalar field background gives us a homeomorphism or local homeomorphism between asymptotic data and Cauchy data in the C infinity topology. So, but of course, I mean, eventually what we want to do, and that is our work in progress right now as well, is to do what we've done here for the coupled Einstein matter problem. And of course, that would be far more interesting than just the fluids on a cosmological background. And it would be really interesting if we could show something like this, so that there is a homeomorphism between asymptotic data and Cauchy data. Would be very interesting from the mathematical point of view, but I guess also in some sense from a physical, philosophical point of view, because it would somehow say that the information contained in the Big Bang is the same as the information contained in our universe at any time or so. Whether this kind of question makes sense or not philosophically or physically, I don't know, but at least we can sort of talk about this mathematically. So I think I just stop here and thank you for your attention. Hope you're not asleep yet. So yeah, thank you.